Why is this crashing? Okay, there we go. So today we're going to have a shorter lecture on getting into some more details with noise. Last week we talked about different sources of noise, and we're going to get into a little bit more of the ways we can describe noise. So not only can we describe noise based on the sources, but also the frequency response. So a goal today is going to be know how we use colors to describe the frequency response. Of noise. Another goal is going to be not just knowing the descriptor of those colors, but being able to quantitatively show that on a plot. And you want to be able to do that based on the descriptor of color that we're going to go over, but also the source as well. I'm going to put little stars here to emphasize some of the goals that are more important than others. Also, we talked about those different sources, but how can you determine if you're having thermal noise effects, flicker noise effects, and the like? It's supposed to be like a little smiley face about your screwed up measurement. And after you determine what types of noise there are, ways to reduce those. And finally, we're going to talk a little bit, some miscellaneous topics about noise, signal to noise ratio in the decibel scale, and also another figure of merit, the dynamic range of your instrument as well, which also relates to the decibel scale. So that's what we'll be going over today, and jumping into the different colors of noise. We're using this description of color for noise as the analogy to the different colors of visible light. So different frequencies of light have different colors, so different frequency responses of noise. We're using that analogy to describe the different types of noise you'll observe with color. So when we're saying color, what we mean by that is the power spectrum of the noise based on the different frequencies. So we went over the power spectrum definition last week, I think. So here, the fact that we have this frequency term here, that's where we're using this term color. So the one that we've been using throughout lab so far has been white noise, Gaussian noise. So the analogy of light, white noise means that with white light that has all the colors present, all frequencies present. Like if you think of white light passing through the prism, then you have the rainbow there. Hence why with white noise, we're saying that it has all frequencies present. Or we can say it has a uniform power density as a function of frequency. So if we wrote this, how does the noise scale, or how does our power spectrum scale in terms of frequency? It's going to scale, I'm just going to write frequency with F here. It's going to scale with F to the 0th power. That means you have a constant value for all of those frequencies. So that's what you guys have been using so far. And it's important to note that white noise is the only one that is uniform for all frequencies. It's the only one. All other colors are non-uniform in terms of frequency. Versus the frequency here. So that's what we're going to get into detail today. So let's start by looking at ones that have more prominent lower frequencies. That's where we're going to start. So those ones are going to be just like lower frequencies are in the redder end of the spectrum and higher frequencies are in the bluer end of the spectrum. Again, this analogy with light, the lower frequency noises we're going to discuss today are going to be red and pink. So red can be used somewhat qualitatively, just like when you talk about red shifts or blue shifts with light. You may hear it be used, yeah, if I can spell right, to describe anything where lower frequencies dominate. And then we'll also talk about pink. Pink's a mixture of red and white, so it kind of falls in between the two. So we'll run into pink noise in the lab, where specifically pink noise being a form of red noise, or these lower frequency noises. Lower frequency components contribute more. And quantitatively, we have that the power density here is going to scale as 1/f here. So that means it will decrease 3 decibels per octave. So based on this power density and this change on the log scale, which we'll talk about a little bit later, it also means that in pink noise, each octave has the same amount of energy. So that means something like if we looked at the frequencies from 40 to 60 hertz versus 4,000 to 6,000 hertz, these two ranges would have the same amount of power. So I guess I can number these. 1 is white, 2 is pink. We talk about lower frequency noises being qualitatively described as redder noises, with pink being one of them. And also red, or sometimes it's also called brown noise, also falling in there as well, where red can be used quantitatively as a term as well. And this, when red is being used as a quantitative descriptor, what that means is that the power density scales as 1/f². And sometimes it's referred to as brown noise as well, not based on this analogy with light, but because you'll see it appear in Brownian motion. Where here, Brownian has nothing to do with colors. Brownian has to do with Robert Brown, the scientist who discovered Brownian motion, who was a botanist looking at pollen grains wiggling about due to the thermal energy that was present. So that has nothing to do with this color descriptor at all. So this will be the third one that we'll have on our list. So pink and red are the two colors that we're quantitatively describing for the lower frequency noises. And also I want to point out that if any of you guys use white noise machines to block out the noise of your neighbors or neighboring dorm rooms and stuff, that if you're using a white noise machine, it most likely probably is a pink noise machine. And I encourage you to look, I think I have a link on the YouTube playlist of, there's a very nice video actually having the audio for these different frequencies of noises. And if you listen to the pink noise, that's actually, I think it's a more relaxing and blocking out type of noise. Like the frequencies you hear during a rainstorm outside, if you want some background noise, would fall under like pink frequencies as well. That's just an interesting aside. The other colors that we want to go over are higher frequency, in the higher frequency ranges. So just with that light analogy, we're going to call these qualitatively bluer noises, where higher frequencies dominate or more prominent. So the one that we want to discuss here specifically is blue noise. And it's obviously the opposite of red in the electromagnetic spectrum. So we would write our power density. It will scale as it goes linearly with the frequency. And there's other colors we could discuss that if we wanted to go into more detail with higher frequencies, like purple noise would scale with F squared. There's also gray, black, which is actually no noise, etc. But we're not talking about these because they're not relevant to electronics, which is the focus of this course and the lab that you're working in. So we can plot, we can also plot these different colors of noise. We can make a noise spectrum plot based on the colors, where we're going to plot this on a log scale or the decibel scale on the y-axis versus the frequency on a log scale as well. And if we make this log-log plot, we can start with our white noise, where it would be flats, where you have, when it scales with F over 0, that's going to be a constant. And then going through our different colors that we discussed, pink would fall off linearly, following 1 over F based on this log-log scale. Red would fall off at a steeper slope since it's 1 over F squared. And then blue would be the inverse of that, pink scaling with F over there. So those are the 4 colors that you should understand how the power spectral density scales with frequency for these 4 different color descriptors. So with this presentation of the noise colors, are there any questions at this point?
I noticed that you have it kind of not like a perfect straight line, but kind of wavering a little bit. Is that meant to represent like the fact that it's discrete data, so it will give you like ideally all of those frequencies with ideally that relationship?
Yeah, I kind of drew it as squiggly because since it is noise, and like when you were looking at the white noise in the lab, noise has randomness. So even when it's representing all those frequencies, usually when you're seeing in the lab, it's fluctuating around, that there's some randomness there as well. So rarely do you see noise where it's just like this constant straight signal where you're sampling it very well and frequently, that the discreteness of your observations and the randomness of the source of the noise, and usually, hopefully noise isn't super strong, leads to that, I guess, waviness that I'm showing here, instead of sketching it like a perfectly straight line. I'm trying to exhibit the realities of the experiment. Any other questions?
Is pink noise at all related to flicker noise?
Yep, you're foreshadowing some of our discussion, I guess, the next slide as well. So we'll get there. Okay. So yeah, Jack's question leads very nicely into the slide. That last week we discussed thermal noise, shot noise, flicker noise, and environmental noise. So based on the descriptors that I just provided of those different colors, what color would you say thermal noise is? You can throw it in the chat or unmute. Yeah, so Riley says white, and that's correct. Thermal noise would be a white noise source. What about shot noise? If you think about the equations that we had and how bandwidth was incorporated in that, what color would shot noise be? So just like thermal noise, it's scaled as the square root of the bandwidth. So shot noise would also be a white noise source. And then for flicker, I think Jack just answered that flicker noise, we said scaled as 1/f. So that's a pink source of noise. And then environmental, we said, was at some discrete frequencies. So could you just, okay, Sophia, raise your hand.
Oh, I was wondering, why does the fact that the shot noise is the square root of the bandwidth, how does that lead you to know that it's white noise?
So there's no dependence on the frequency that you're using. So it's going to be equal for all frequencies. So both thermal and shot noise, since that bandwidth term is in the equation, that's why it's a white noise source.
Thank you.
And then finally, with the environmental noise, I could wait and try to trick you guys to saying a color with environmental noise, but since it's at discrete frequencies, it actually has no color assigned to it because it doesn't have a linear or an inverse dependence or constant dependence there. So another way that we could plot, make a noise spectrum plot could be based on the sources. So previous slide, we just showed it based on the color. Here we want to show it based on the sources. And this is an important concept to know for Lab 4, Quiz 4, and the like. So we're going to make a similar plot again, where we have our spectral power density on the y-axis on the decibel scale and the log of the frequency on the x-axis. And we can draw each of these individually, that if we included thermal or shot noise, it would be a constant line. So actually, if we wanted to draw all of these individually, we would kind of say like, okay, there's thermal noise. We can also draw a line that's going to be like shot noise. Each of those components would be their own constant value there. Flicker noise, last week we described that it goes as 1/f, and it's only significant less than 100 hertz, so only at the lower frequencies. Once you get above 100 hertz, its contribution is quite minimal. So we could draw the flicker noise there. And then environmental noise would be at very discrete peaks. So we talked about with the AC power supply that you see 60 hertz show up. At higher frequencies, we talked about the range for AM and FM radio that may interfere. You could even see, depending on how sensitive your measurement is, you can even see lower frequencies based on if, like, let's say there's a class change and it wasn't COVID and a bunch of people are walking around, you can see very slow vibrations show up. So that's why you'll see many experimental physics labs being in basements, more prominently, I guess, for optical measurements, but to even remove any effects of vibration. Like I know when Professor Strangi renovated his lab here, his lab's right next to an elevator, and they actually did measurements of how much noise would the vibrations of the elevator when it's running introduce to the measurements in his lab. So there's a lot of different sources that you can have for environmental noise. So this is drawing each of these sources individually, and you can then add all of these together to have your total noise spectrum over the entire band. So you can see here, okay, if you're taking a measurement below 100 hertz, you may run into issues with flicker noise, and specifically at 60 hertz, you could have environmental noise. This flat line here is primarily the contributions. This offset is due to the thermal and shot noise. So if I draw both of those sources, adding them together shifts that up quite a bit. And then the other sources for environmental noise. So if I ask you for a noise spectrum plot that you might have in lab, you probably want to draw something like this versus the spectrum I drew on the previous slide is based on the different colors of noises, but that doesn't have to do with any of the sources or an actual measurement that you're doing in the lab. So any questions with sketching out the spectrum of different noise sources? Okay. So next, we're going to talk about getting into a little bit more detail about these different sources that you may encounter of noise. So how can you tell if you're having thermal, shot, flicker, environmental noise in your measurement? And if you identify that, how can you reduce it? So last week, we can start with thermal noise. We're going to go in the same order as last week. So this is a little bit of a refresher as well. We define that thermal noise you'll see in your voltage measurements, and it'll show up as 4 kVt times the resistance times the bandwidth. So again, remember kV is Boltzmann's constant due to the thermal fluctuations. T is your temperature, R is the resistance, B is the bandwidth as well. So based on these variables, which ones could you modify in the lab to see if you see a reduction or increase in the noise? That's a way that you can identify it. So out of these variables, which ones can you change? You want to throw that in the chat or unmute?
You can change the resistance.
Yeah. So one way that you can check is look at the resistance. So if you vary it and see the RMS of your noise scale as the square root of R, that's one way that you can identify, is it due to thermal noise? Any other variables in here you can change? Yeah, so Riley says R. You can change the bandwidth. That is an option, but I will note bandwidth is harder to vary. It's okay. It's okay, Riley. It's more challenging to vary. And you'll see when we discuss shot noise, it's hard to distinguish one source of white noise versus another. Sorry, my chat window is over here. So if you're trying to identify, here we're going to be talking about like identifying noise. Bandwidth probably isn't your best knob to turn to identify that, but it is something you can vary, but not to identify thermal noise. And then the last one that Robert points out is temperature that you can change. Does it scale? So vary, does it scale with the square root of T? So for some measurements, it's easier to vary temperature than others. If it's something small that you can submerge in, like, let's say liquid nitrogen or liquid helium, that's going on in research in like Professor Roll's group. Professor Gao's group, Professor Cash's group, they all work with those cryogenic liquids. Then it's easy to go from room temperature to those ultra cold temperatures. And if you see a difference or a reduction of noise, that would be a way to identify that. So identifying thermal noise, resistance, and temperature are key ways to tell, is it thermal noise that's affecting your measurement? And then if you want to reduce the effects of thermal noise, that's where bandwidth can come into play. So reducing the effects of thermal noise, there's 3 options here. So one, like I mentioned, is do your measurements at cryogenic temperatures. So that would be like nitrogen or helium in liquid form, if you can do that. That's one way to reduce that effect. Second one is you can lower your resistance and the impedance of your sources. And then the third one is where the bandwidth comes into play. You can use filters to reduce the bandwidth. And then of course, thankfully, none of you guys suggested to change kV. We can't change Boltzmann's constant when we're dealing with thermal noise here. So these are the ways to reduce thermal noise effects. And they most predominantly come up into play if you're doing like very low voltage measurements, maybe on the scale of nanovolt signals. That's why like in Professor Gao's group, where they're trying to do like electrical measurements on little nanowires, yeah, you're gonna have very low signals there when you're working with those type of materials. So that's thermal noise. We're now gonna shift gears to shot noise. So we're calling the equation we wrote last week. You will see this show up in the current instead. And again, our equation square root of 2 times the fundamental charge of the electron times your current, your direct current value, and your bandwidth. So with shot noise, you're a little bit more limited of how you can identify shot noise, because within this equation, the variables that we have, we already mentioned bandwidth isn't really the greatest, just like in thermal noise. That varying the bandwidth, how would you be able to tell if it's the effects of shot noise or thermal noise? So left in this equation is the only term that's left is your current here. So you would vary your signal strength and see if you have that square root of the current behavior to identify if shot noise is your problem. So that's how you would ID shot noise. And then the way that you would want to reduce shot noise is one, if it's possible, you can reduce your current. But shot noise is mostly significant when you're doing measurements, maybe like at picoamps or femtoamps. So it's very hard to reduce your current further. So a more common option is to use ensemble averaging. I'd say that's a predominant way. And then finally, the third one, just like with thermal noise, if you can reduce your bandwidth by using filters. So that's for shot noise. And I want to quickly go over so you guys have enough time for your quiz. The last 2 noise sources, continuing on with this, is with flicker noise. where again, scales with 1/f. Since there's not like a well-described source of flicker noise, it's a little hard to remove. But one thing that you could do is, can you move your measurement to higher frequencies? So if you can take a measurement above 100 hertz, that would be a great way to do that, work at those higher frequencies. If you're stuck working with a lower frequency, you can modulate your signal. So you might think of something like a chopper. I know with optical measurements, like it's literally like a fan looking something that will chop your signal. So it's being modulated at higher frequencies. Electronically, can you switch it on and off very fast? So then you're shifting it to a higher frequency. And another source, even though we don't really understand flicker noise that well, you can vary the electronics. So if you use like carbon resistors versus carbon film, they've been known to have different 1F, different flicker behavior. Where carbon, based on the quality of that carbon, you're going to have different 1/f behavior. So carbon film is higher quality, more expensive. You'll see less flicker noise components there compared to bulk carbon that's cheaply made. So those are some ways to remove it. Identifying it. We've mentioned seeing that below that linear behavior below 100 hertz. So I'm not as concerned about identifying this source. Then finally, environmental noise. So the way to ID it is, do you see it at very specific frequencies or bands? And especially if it's always there, if it's repetitive. I was just talking with the spectroscopist that they were always seeing with like a time resolved measurement, always exactly at 20 nanoseconds, they would see this stray peak. That's really the fact that it's just a stray random peak and it's always there. And no matter what the sample is really pointing to that it's environmental noise. And they ended up finding that the laser was bouncing off of something within their black box instrument. And they were just looking at the time it took that laser pulse to hit that reflective surface and come back to their detector. So they were seeing that. So the way to remove environmental noise is you can use electronic shielding. So if you know you're going to be doing some measurements and there's going to be interference with the radio waves, putting your instrument in something like a Faraday cage to remove that is a way to remove environmental noise. So this really relates to, for the physics engineers in the class, like designing early and being strategic with the design of the electronics that you're making. Can you incorporate a Faraday cage or some electronic shielding there? Another option would be if you can work with different types of filters. Notch filters would be something that would be like the inverse of a bandpass filter. Where can you filter out a very specific band of frequencies instead. And then of course, with all of these, we've also talked about like software methods or post-processing. So can you do averaging? I mean, we talked about filters that are hardware. You can do corrections. Like if you know there's always this repetitive peak that you're seeing with environmental noise, can you measure it really well and always subtract it from your measurements? These are all different other options of reducing noise sources. So any questions with that section of identifying different noise sources and removing them?
I have a question about the flicker noise.
Mm-hmm.
What is the difference between moving a measurement to higher frequencies and modulating it to higher frequencies?
So yeah, I would say moving would be like, okay, let's say you're in our lab and you're like, oh, I'm just going to pick some arbitrary frequency. I just need some sine wave. I'm going to take that measurement. I'm going to do a really slow sine wave at 10 hertz or something. But maybe the magnitude's small. And then you're seeing effects of flicker noise because you chose that lower frequency. If that frequency is just kind of arbitrary and you can easily shift it to 1 kilohertz, then you would want to select that. So that's like if you have the control to do that with whatever you're trying to detect. But let's say modulating the signal is like you can't, whatever you're measuring is occurring at a low frequency. So there's no way that you can force it to physically change in your sample and make it go to a higher frequency. So that's what I mean by the difference between like moving, that would be like the design of your experiment versus modulating, like there's a physical limitation in what you're doing. So can you take that low frequency process and then somehow design it so you can shift it to a higher frequency, like what I mentioned with that chopper. And I'll have to think of a specific example with modulating the signal. I can think of ones with, like I keep giving optics examples because that's what I work with. I'll have to think about one that's more electronic and I can throw that up on Canvas or talk about it tomorrow in lab.
Thank you.
Any other questions? Okay. Now, this is the last slide. I'll skip the next one and talk about it in the next week. That I did want to just mention again, signal to noise ratios that last week or 2 weeks ago, we talked about reporting it as the average over the standard deviation for something that would be Gaussian. But it is also useful, and I think you are working in lab 4 a bit and possibly in lab 3, a little bit of reporting this in the decibel scale. So signals can fall over a large range. And then that's why a log scale may be useful. So instead of reporting as just the average of the standard deviation, if we wanted to include this on the log scale, this may explain a little bit of some of the numbers that I threw up earlier. We can write this with the decibel based on the voltage of your signal squared over the voltage of the noise squared on this 10 times log base 10. Or we can also write this as 20 times the log of B signal over B noise. So that just a reminder that you can report signal over noise on this log scale as well. So again, that 3 decibels would be half power. 6 decibels would be at half the voltage, which we described, I think, in the first lecture as well with the decibel scale. And like you guys have derived in one of the labs, that you use the ARB, and more specifically the DSO, when you're using the decibel scale, it's referencing 1 milliwatt of power based on the 50 ohm input reference or internal resistance there. So those are the important specs for your dBm scale that you see on the DSO. So just wanted to mention this in lecture in addition to what you guys have derived in lab earlier, and you should have seen that in the solution guide, but reporting signal to noise ratio on the DSO with that scale. So in interest of time, I'll stop there. Stop.